Hello, good evening. I hope you can hear me. So just let me share my screen and one of you can give a feedback whether you can see it. So today we will be discussing about the citizen science programs of EKC, which is a project under Inter-University Center for Astronomy and Astrophysics. So I'm an astronomer there, and I work in the as a software engineer and a data manager for the data cluster, GPU cluster at Ayuka. And I am very actively involved in designing all these citizen science projects and also running them. So can somebody tell me whether you can see my slides? Whether you could see my slides earlier? Okay, fine. So I'll put it in the slideshow mode now. Is this better? All right. So let me tell you a little bit about PKC. So PKC, or Pune Knowledge Cluster, is a knowledge cluster or a Section 8 company established by the Office of Principal Scientific Advisor to the Government of India. So in 2021, the PSA was Dr. Vijay Raghavan, and he was one of the pioneer, or he was the one who initiated and appreciated this idea. So currently, it started at that time. It started as a project under Ayuka, where Dr. Ajit Kembhavi and Dr. L.S. Shashidhara from ICER co-wrote this proposal, and it was set up as a Ayuka project. Now it has spawned into an independent Section 8 company, and Pune Knowledge Cluster was the first cluster set up by the Principal Scientific Advisor's Office. Now there are 6 more clusters: Delhi, Jodhpur, Bhubaneswar, Bangalore, Pune, Hyderabad. So all these clusters are actively working, and there are a few more clusters coming up. Now PKC is involved in all these areas that you see on the right hand side. So I work in the big data and AI vertical, which includes projects related to astronomy as well, this being one of it. So today we will be talking about 1 million galaxies, and 1 million galaxies, the name is given because the ultimate aim of the project is to create a accurate catalog of 1 million galaxies of various features. So the features of the galaxies will be identified or separated on the base of their appearance, or what we call as morphology. So there are various kinds of galaxies. We will be talking about the intent and why are we doing this project in the first place, because there exists a project already on a platform called Zooniverse. So what are we doing differently here? We'll also talk about that. So when we talk about astronomy, the data sets indeed are astronomical, both literally and figuratively, because the data sets that telescopes generates is in the form of images, spectra, and all different kinds of data types. And this can go up to few hundred terabytes. So currently we are using a catalog called SDSS, which is and we are also using the images generated by a telescope called Subaru. So this is a Japanese telescope which is about 8.2 meter diameters, and it is stationed at Hawaii. And we are using images from a camera called Hyper Suprime Cam, and it produces extremely high resolution galaxy images. And the idea of this project is that we will use human resources and citizen scientists to look at different images of galaxies and help us understand or help us classify them based on their appearance, whether or not there is a spiral in a galaxy, whether or not there is a bar in a galaxy. So all these names that I'm telling you are the different features or the different ways in which a galaxy is classified, and we will be talking about that. So now all these observatories have generated tremendous amount of data, and it is not possible to automate the classification right away. As soon as the telescope captures a picture, what you can do at the most is do an astrometry of your image, where telescope image can be calibrated, the pixels of your image can be calibrated to the coordinates in the sky. But it is very important to understand the population of the galaxies present in your image, and it is also important to understand their evolution. So if you were to study a human being, and if I would have asked you that, tell me about all the stages of evolution in humans. How does a human grow? How is a human born? How does it grow, and how do they die? So there are two approaches. One is to take one particular human right from the human's birth all the way up to the death and study each and every stage of their life. Or a faster approach is you look at too many humans So they will have various age groups. They will be at various stages as a part of their evolution, and then you can reach to a conclusion sooner rather than later. So that is exactly the idea. You all know that the galaxies and stars live for billions of years. So it is practically impossible to study evolution of one particular object. But we take the second approach where we look at all the sources that we can, and we look at them at as much better resolution as possible, and then we take help from citizen scientists to classify these galaxies. And what happens afterwards is we use the labels, or we use the answers of the citizens to train different neural networks or different AI networks, and then we try to automate the classifications with the help of computation. So now when we do this, this can be done 24/7, 365 days, and a lot of data can be crunched with the initial knowledge that was given by humans, which is called as the training data. So we will also discuss a little bit about that. So all in all, we are dealing with hundreds of gigabytes of data. We will be showing cutouts of thousands and thousands of galaxies. And once we get a significant amount of answers from citizens, where the answers are sufficient enough to train a machine learning model, then we will the model will take over, and then it will try to classify the new upcoming images as fast as possible. And ultimately, we would like to release a catalog of 1 million galaxies. And this catalog will be a very important base catalog for a new set of observations that will emerge from these new generation telescopes, which include the Vera Rubin Observatory or the Large Scale Synoptic Telescope, also the 30-meter telescope, which is scheduled, and then there is a giant Magellan telescope, and so on. So we will also discuss about all these projects. So speaking of galaxies, so it is important to understand what a galaxy is and how the galaxies look in order to effectively classify them. So this is the anatomy of Milky Way. If there were a way to take a selfie of our Milky Way galaxy, it would have looked like this. So this is, of course, an animation. You cannot really look at the galaxy from outside, but you can look at different parts of the galaxy and put all that information together to understand what is the structure of our galaxy. So we look at the motions of the stars within our galaxy. So all the stars that you see in your entire lifetime, all the individual stars are all a part of our galaxy. In addition to that, we also see some interesting features like globular clusters, which also are a part of our galactic halo. And then there are also other objects like open clusters and so on, so which are indeed a part of our own Milky Way. Now, when we look at our Milky Way galaxy, if we were able to do it from outside, it would have appeared like a barred spiral. So, and we lie on one of the spiral arms, roughly about 2/3 of the distance from the center. So we are a part of our solar system, where our sun is a moderate star. It is not too large, it is not too small. However, this graphic represents you the approximate position of where our solar system is and how the galaxy structure is. So we would classify our own galaxy as a spiral, as well as it would have a bar at the center. So it would together be called as a barred spiral galaxy. So this classification was first done by a person called Edwin Hubble. So he's quite famous for being named after a telescope being named after him. But he did some remarkable work in studying the distances, also the cosmological redshifts, and so on. He gave us the Hubble's constant, which helped us understand that the universe is not only expanding, but it is accelerating. So going further, this is another example of a beautiful spiral galaxy. It is called M51. It is basically a clear spiral. This is a photo taken by Hubble Space Telescope. So this is a integrated image. Integrated meaning the light over a large period of time has been added, and hence you can see such beautiful features. Now, what is happening with this galaxy is not only it is a spiral, but it is merging with another elliptical galaxy, and it is eating off the matter, and it is merging it into itself. So this is a beautiful example of a merger happening, and it was first discovered in 1845. Now, this is another example of a beautiful galaxy called Andromeda. So Why am I including Whirlpool and Andromeda is because you can see them through small telescopes as well. And if you like, you can capture them with your simple DSLR cameras as well. So these are some classic spiral galaxies. Now, take a look at this one. This is, although this is a spiral, it does not look as magnificent as Whirlpool because we are looking at it from an angle. So if you were to further tilt this galaxy, then no matter whether it is a spiral or a bar, it will look like an edge-on galaxy. So edge-on is another feature that we classify when we show you different images. So we are just looking at some good examples of galaxies. So these are some more types of galaxies which are barred galaxies. So you can see there is a classic bar in the center of all of these galaxies. Then the galaxy on the bottom right hand side is called a lenticular galaxy. So it is kind of an hybrid between the spiral and bar. So it is the stage which almost lies on the boundary. So you can see a clear bar in the center, and then you can see some spiral arms emerging out of the edges, and the spiral arms have nearly joined. So and the central part looks like a lenticular shape. So hence it is a lenticular galaxy. Now this is a galaxy captured by James Webb Telescope. It is a NGC 143T, and it is a barred spiral. So you can see the spiral arms are quite bright at the center, and then there are huge dust lanes, spiral dust lanes, which are emerging outward from the galaxy. So it is a highly detailed image. It is taken in near infrared. And then there are elliptical galaxies. So in our catalog, we call them as smooth. Smooth and elliptical in case of our catalog is the same thing. So this is the largest and the brightest galaxy in the Virgo cluster. This is the galaxy M87. You might have heard this name before because the famous black hole image was captured. The supermassive black hole at the center of this galaxy was captured, and it was quite famous. So this photo is extremely old. It was captured by David Malin. Those who don't know, David Malin is a legendary astrophotographer, was a legendary astrophotographer. And this is M87 captured from Australia, so near the Parkes Observatory. Now, this is what I was talking about. So this is called as a tuning fork diagram. This tuning fork diagram is used to classify the galaxies based on their morphology. Now, this was first given by Hubble, and these numbers are for cataloging or understanding for our research purposes. But you can clearly see that the galaxies on the left are elliptical, the galaxies on the rightmost is irregular, and then the tuning fork separates the bars as well as spirals. So you can see there are barred spiral galaxies on the bottom, and then there are spirals on the top. So we would classify our Milky Way galaxy as a SB type, which is on the top, which is a barred spiral galaxy. Likewise, you can look at all sorts of images, and then you can crudely classify the galaxies within this tuning fork diagram. Now, these are some examples of lenticular galaxies that you will see in the catalogs. Then these are some beautiful examples of rings. So rings are another other peculiar features that you can observe. So when we are going to show you all these images, what we usually do in our platform is, I will be showing you the platform as well, is that we give you a set of reference images on the top. And by looking at the reference images, you can understand what all features are present in the given image. So it is expected that you compare the given image, look at it very carefully, and you identify all the features that you see in a given image with the help of the reference images given in the top. So you see there are some beautiful ring galaxies, and there are a lot of interactions and interesting astrophysics or the gas mass transfer going on in some of these galaxies. Some of the galaxies are clear rings, and it is remarkable because this project is also exciting for me personally, because you will be looking at galaxies which nobody has looked at before. So of course, many telescopes keep on capturing the sky surveys. They look at the sky multiple times, but nobody really looks at the images the way that you will be looking at them. So you will have a great opportunity to look at some beautiful features. There is even a possibility that you might discover something entirely different. So I will show you one example of such a case. So these are some more examples. So this is a dust lane elliptical galaxy. So the galaxy itself is elliptical, but in the central part of the galaxy, there is a dust lane, a classic dust lane that you might be able to figure out here. Then there are tidal tails and bridges. So whenever the galaxies are merging or whenever the galaxies are passing by, some galaxies may pull off some mass from the other galaxies and create these tidal tails or bridges. Or there could be mergers. Either there could be ongoing mergers like M51 type, or there could be some advanced mergers going on where the galaxies may pass through each other and the matter inside the galaxy might be interacting with each other. So we expect something like that to happen with our own Milky Way galaxy and our neighbor Andromeda. So in another 2.5 billion years, we expect that the Andromeda and Milky Way galaxy will merge, and they are very, very likely to pass through each other without collision of too many stars. And currently, by looking at the blue shifts and the existing data, we do not expect anything to go wrong with the solar system so long as the sun is intact. So we don't need to worry. Also, it is very far from now. It is not going to happen anytime soon. So this is the central part of the image is the Hubble deep field. It covers about 1/13 the size of the moon. So it is a very, very small region in the sky. So with the ground-based observatories, when we looked at the sky surveys, we found a region near the north which was not very rich in galaxies. So we decided that let's take help of Hubble telescope and let's integrate the image or let's integrate the light coming from that area for about a month. And then when the final image came out, this beautiful deep field image was taken. This image was captured in 1996, and this is called as the Hubble deep field. And each and every dot, apart from the ones which show diffraction spikes, the ones which are showing these diffraction spikes are called as are basically the stars. All the other dots that you see are individual galaxies. So you can see how what a tremendous amount of galaxies are there in the universe, and those are waiting to be discovered by going deeper and deeper inside the into the fields. So we currently estimate about 2 trillion galaxies are there in the observable universe. And post Vera Rubin telescope, which is an upcoming telescope that is expected to be set up, the LSST survey will add billions of highest resolved galaxies. And the one galaxy image that Vera Rubin Observatory will generate will be about 3200 megapixels. They have an incredibly large camera. So after my session, you can go on the internet and you can read more about the LSST or the Vera Rubin Observatory. And this will generate tremendous amounts of data. So currently, the SDSS catalog, which is the Sloan Digital Sky Survey catalog, so it comprises of 18 data releases. I think now there might be about 20. The data release 18 had a data of around 657 terabytes. Now, this is the entire data that SDSS catalog has captured so far. Vera Rubin Observatory will generate that data in a single night. Now, imagine we are taking so much efforts and time to process and classify the galaxy images from SDSS catalog. Our project, the 1 million galaxy project, has been running for about a year and a half now. And we have been able to look at 2 lakh or 3 lakh responses. It's about 2,90,000 responses so far. So imagine if we were to get the data from Vera Rubin Observatory, which would generate few hundred terabytes of data per night, then we would definitely need a processing pipeline and some automation where we would be able to catalog the galaxies captured by such telescopes. So this is the main intention, or this is the main reason why many different astronomers are designing their citizen science projects. So citizens can really help create good training data sets, and these training data sets will be very, very useful to automate or to set the telescopes on an autopilot mode for good quality classification. Now, just creating a catalog is not enough. You need to understand whether the catalog is good in quality. So at what confidence, at what percent confidence can you say that the spiral chosen from a catalog will really be a spiral? So whether you can say it with 95% confidence, with 99% confidence. So all such statistical data also should be present along with the catalog. So the researchers can pick a particular catalog of galaxies, and then they can run different physical models to understand the evolution of the galaxies. So we basically are interested in looking at all such data coming from the ground-based as well as space-based observatories. There are a couple of projects in pipeline at PKC where we are collaborating with a lot of astronomers from IITs and NCRS. Currently, we are already working with astronomers from Indian Institute of Astrophysics, where Sudhanshu Barve has designed this project, and Ajit Kembavi from Ayuka. Both of them together have designed this project, and we have been running it successfully for quite some time. Now, there are new advanced capabilities. The telescopes are being upgraded. We have the state-of-the-art telescopes already, but now we have evolved. We are now launching more and more telescopes in space, and we are upgrading the facilities on the ground. So you see the multi-wavelength telescopes are given here. There is Hubble, Spitzer. So Hubble is visual. The Spitzer is infrared. Then there is Herschel telescope. There is Galax, Newton, and Chandra. And all these telescopes are working in various wavelengths. They are generating tremendous amount of data. And because of all these new observatories, the data deluge or the data flood is going to be hitting us very soon. So instead of terabytes, now petabytes of data is going to be available. And it will be very important for us to understand and effectively work around with the data without losing information. So the data mining is indeed a challenge, because you need to mine only the useful information from a large chunk of data. And you all will agree that we will not be able to store the raw data for a very, very long time. So our algorithms should be very good quality algorithms where they will be able to extract data in near real time, and we can keep observing throughout multiple cycles. So this is where the citizen scientists come in. So the citizen scientists are really, really important, because they have to do the tough kind of a work which is kind of repetitive. So now when you are looking at galaxies, if you are interested in astronomy, and if you are excited about looking at different galaxies, what happens here is humans tend to capture features which computers many times can't. So our eye is usually trained to look for discrepancies or look for similarities or differences better than a machine can. Once you train a machine that whether a particular feature, this is the kind of a feature that you should be looking at, then the machine will perform well. But unless the training data is ready, we do need citizens to actually look at the data and look at some interesting objects, which help us undertake new observations and undergo different discoveries. So we have a large number of people which contribute to the PKC citizen science projects. So we have citizens vigilance as well as curiosity as our biggest strength, because we get participation from many members of this group as well. But in addition to that, we get participation from colleges, schools, and we tend to do outreach programs in collaboration with Ayuka, which is our parent institute, and we travel to all parts of the country, and we do outreach about various citizen science programs that Ayuka and PKC run. So the strength of this platform is it is basically open to all. It is very simple, very intuitive. It is just a checkbox form. So you have to look at a galaxy image, then you have to compare the reference images given in the top. And whatever feature you see, you just mark yes. If you do not see a feature and if you like, you can mark no. So just like how having a feature is an important classifier, when you mark that a particular feature is not present, that data is equally important for astronomers. So we have tried to capture that as well. So if you sincerely select yes and no for a particular feature, it will help train the machine learning model faster and better. So there will be no ambiguity. So let's say there is an image A, and you look at the image and you see that there is absolutely clear spiral inside the image in the galaxy. So you mark yes for a spiral and you mark no for all other features. Then the machine learning model will be absolutely certain that, okay, this user has marked yes for a spiral feature. So whenever I look at such a galaxy, I know that it is a spiral only galaxy. If you mark spiral as well as bar, then the machine learning model will eventually learn that, okay, this kind of an image will be, I will call this kind of an image as a bar spiral galaxy, and then any other images consecutively which will appear, which will be similar to this image, will again be classified as bar spiral. So this is the kind of the data flow or the workflow. So whatever I just said is written in the form of a neural network, or we use different data sets, and we try to create different training sets, and we test all those training sets on some controlled images. So like I already said, we are using the images from the Subaru telescope. So this is the link on the top right. I will be sharing the QR code and the link later on again. So this is basically the 1 million galaxies project. And so we have partners and beneficiaries from all over the country. We have project students and interns who actually keep on designing and upgrading the web page. They also keep on designing and upgrading the AI models that we use in the backend. There are students which also do statistical analysis, and they try to understand what are the kind of citizens which are participating, what are their engagement levels, how is their accuracy level, and what can be changed to facilitate more participation from a particular group of citizens. And we also have a very good statistical data on that. So I will also highlight a little bit about that. And of course, we have science enthusiasts and citizen scientists like you all, where you all actively participate. The moment we add more galaxy images, there are at least 50 to 60 citizens which we know are very active, and they get it done within a week's time. So we really need such enthusiastic participation, because the sooner the better the galaxies are classified, the sooner will be the sooner will the machine learning model be ready, and we will be in a position to automate all these classifications and reach the 1 million galaxy goal faster. So we have the knowledge partners as IUCA, NCRA, II, and HBCAC. And we also have publicity partners and members from astronomy clubs, planetarea, and all other groups of schools and colleges. So this was our basic timeline. Our pilot project was launched, or the pilot website was launched in 2021 August. And then the website was upgraded. The interface was redesigned and upgraded in 2022. And currently we have received about 290,000 responses, and we are actively looking at active engagement and active participation from almost people from all of the India. So we used to conduct these online sessions in the COVID time, where people from all parts of the country would participate. We would train them on different kinds of morphologies of galaxies. We would also tell them about the different applications of the data sets that they are creating. So what all can we understand by simply having the population of galaxies in a particular region of the sky? And it can tell a lot more about the science as well as the physics which is underlying within the galaxies. And once you provide a good quality data set, a scientist can work without any ambiguity and without any worries that the quality of the data set is ensured. So that is our goal. So we want to create a data set with about between 95 to 99% confidence for all these kinds of features. So this is the interface. So like I mentioned, there are reference images on the top. On the left hand side, if you click the image pops up and it zooms in to help you see the features better. Now on the right hand side, there are all these features, and there is a yes no radio button which you can choose. If you see a feature, you select yes. If no, then you select no. And there is another very important box at the bottom. So if you see a feature which is not listed in the galaxy image, in the interface, you can write your remarks over there. For example, in the bottom image, there is a blue dot. So this blue dot could be for various reasons, but there is no option as a blue dot in the options that we have given. So you can add additional information on the unlisted feature menu at the bottom. So there is another profile page where you can see the number of galaxies that you have explored and you can also see how many galaxies are remaining. And at any point of time, you can download the participation certificate, which will mention the number of galaxies that you have explored using the Citizen Science platform. So for those interested in the technical aspects, we have this as the backend, and we have designed this website completely based on Django and Python, and the templating is done in pure HTML. The database used is a MySQL database. Currently, 6 gigabytes of data is used for mainly for images, and the website is updated regularly with new data sets, and the validation of the answers is done by scientists to train the AI algorithms. So there are some control images that we have introduced where we know the answers to those images. Based on those images, we can understand the performance of the citizens, and then we can also help group the better performing citizens. So let's say even if a few number of better performing citizens agree that a galaxy has a particular feature, we can simply classify that galaxy and remove it from the data set. So not too many people have to look at the same galaxy again and again. There will be more number of classifications that will be done. So these are some statistics where how many amount of males and females have been participating, how is the distribution of students, working professionals, citizens, senior citizens, and so on. So this is a slightly old data. This is about 6 to 8 months ago. This is another statistical plot where it shows the distribution based on the states in India, and then there are 27 members or 27 participants who are registering from abroad. So based on the answers that we have received, so we understand that there are naturally more number of spiral galaxies that have been classified, which is also the case in nature. You find far too many spiral galaxies naturally in the catalogs, followed by bars and interacting galaxies. So this is the distribution from whatever data set that we have uploaded, and this data is again slightly old. Currently it is 290,000 plus features have been classified. So based on that, we have generated all these insights. So let's not get into this right now, but the final goal is to create catalogs of images with more than 95% confidence, and the spiral images that we have taken, we have grouped them into 30 responses, and then we have created multiple bins, and then we have seen how the citizens perform. So from this analysis, the long story short is there are about 30 to 50 responses are adequate to categorize a feature with 95% accuracy. So this is what this is the whole reason for doing this exercise. So we created bins of 30 and bins of 50 from whatever number of responses we got for individual galaxy, and based on those responses we found the probability, and based on that probability we understood that between 30 to 50 responses are okay or enough to understand what is the feature present in that particular galaxy. So after 50 responses, we can remove the galaxy from the catalogs. And just by the statistical analysis, we will be able to classify the newer galaxies. So these are some testimonials from the citizens that have participated. So in these are the last 4 or 5 slides that I want to show you. This is a very interesting story because it will apply to you all as well. So this is the story of Hani and the mystery of the Furep. So Furep is basically German or is a European word for a frog. So this is Hani. So Hani van Erkel is a Dutch teacher. So she was participating in a project by Zooniverse called Galaxy Zoo, and she was classifying the different galaxies shown in the image. So in one of the images, she saw the image of galaxy IC2497, and just below the image, she saw a particular blob or a green blob that looked like a dancing frog to her. So because of that, she mentioned that there is a Furep, VOOERWERP is pronounced as Furep, just below the galaxy. So, and she also mentioned that the Furep looks like a dancing frog. Now, based on her answer, so we can clearly see it that there indeed is a green blob next to the spiral galaxy. And that was an additional remark that she had mentioned. Just like I had told you that you can mention the unlisted feature, you can choose an unlisted feature checkbox and mention additional information. So based on her response, then when the astronomers looked at that flagged image, they had all these questions: whether is it really real? Is there anything else like it? Whether is it local, or did a supernova create a loop? Does the Furep or does the blob contain any stars? Is it just an unusual nebula? Is it a weird galaxy formed from some or the other kind of merger? And where is it? Is it closer or is it at the edge of the universe? So all these questions came into mind. And then what the astronomers did was they looked in the past catalogs. So Furep was indeed first imaged in 1953 as a part of the DSS, or the Digital Sky Survey, the prior to the SDSS. So this image was captured in 1953. Now you remember, like I mentioned, nobody had actually looked at these images. So the Sky Survey had captured these images, and we have Sky Surveys from going back right from the 1950s. And in the old image taken by the Palomar telescope, this feature was found. So based on that, we were able to conclude that it is indeed real. Although nobody had noticed it before, it existed. So the image is not, it is not a sensor artifact, or it is not some defect which was captured by the Subaru telescope. The object is really there in the sky. Then this tiny spot was observed again by astronomers using newer telescopes. And based on the newer observations and based on all these detailed observations in multiple wavelengths, we finally understood that, okay, we know what this object is. So this is how the object got created. So the spiral galaxy IC2497 was moving, and it started interacting with a passing galaxy. Now, when the passing galaxy came close to the IC2497, the black hole in the center, which is also called a quasar, got activated, because it was able to gravitationally activate the active galactic nuclei in the center. The quasar got activated, and a streaming jet of gas started to emerge from its poles. So one of the streaming jets fell onto the gas and the dust which was surrounding the IC2497. And this IC2497 surrounding gas was charged, and it was basically ionized, highly ionized. And then it gave, it triggered the star formation in that particular nebula. And the nebula started getting illuminated, or it became an emission nebula and started emitting radiation. So this is how the Furep, or this object, is officially called as Shahani's Furep now, because she discovered it. So and this discovery was made because of the participation of common citizens in astronomy research. So this object would have gone unnoticed if Shahani had not seen the image. It would have probably taken few more years to discover that such objects exist. And based on this information, we were able to find many other examples of Furep-like blobs around other galaxies as well. Now, this kind of ionized part of the tidal tail is officially called as Shahani's Furep now. And this was a completely brand new discovery. This was an object that we had not known before, and this was discovered, and this was found only because there was citizen science participation, and somebody took their time and actually looked at the image very carefully and reported whatever they saw inside within that image. So finally, we acknowledge all the contributors. So the citizen science projects are important and useful only if the citizens give correct answers. So it is not about speed, it is about quality. So whenever you are participating in any citizen science program, don't worry about how many galaxies you were able to classify. try to worry about how many galaxies you were able to classify correctly. And that is crucial because that completely changes the dynamics and the time scales within which the citizen science projects can be concluded. Because although the citizen science projects are ongoing, it is important that the data quality is good. If it is not, if the answers are given at random, then the machine learning models will get confused and hallucinate, and they will take longer time to learn and unlearn these mistakes and learn the correct classifications and identifications again. So the technologically sound citizens can be part of a project. If you are interested, you can join us. You can not only classify the galaxy images. If you would like to download our codes and run your own AI algorithms on it, try out your own classifications, you can get in touch with us. We would be very happy to share our data with you, and we look forward to some exciting results. So the idea behind the citizen science project is always to open source and make their data available to the public, help them understand the data sets, and with their help, we ourselves can understand our data sets better. So these are the mitigating challenges. So the consistent citizen engagement and momentum is very much required. Then we also need to fix the inaccessibility problems. So the apps, usually whenever you design an app or a website, it should ideally be multilingual, so it simply reaches more people, and people are more comfortable in their local and languages that they clearly understand. And the platform should be designed in such a way that they should be fully customizable, and they should be one should be able to diversify the same platform. So the same platform that we use for our citizen science project of galaxies, tomorrow we can use the same existing framework, the backend as well as the platform, to classify flowers, for example, different kinds of flowers or different kinds of butterflies. The idea is to make the platform as scalable and as diversified as possible, and it should always have consistent engagement. So outreach effort should be taken. So this is our last slide where this is our vision. So we want to bring out the community aspect by supporting the interaction between scientists and citizens. We want to facilitate wherever possible to help citizens understand what we do. And we would like citizens to participate and give us suggestions and inputs on how we can effectively transfer our learnings to you, and how you can comfortably participate in such kinds of citizen science programs. So this can be a beginning of our conversation, and we will always be in touch. But if you have any inputs, when you go back, you take a look at the platform. Please suggest your inputs. And if you would like to participate in designing or upgrading the look and feel of the web page, or even in the backend process where you actually design the AI algorithms, or you optimize the AI algorithms to work better, so all sorts of participations are encouraged. Then finally, the data is open for all, and we are here to provide you for any kind of a support, may it be computational, may it be for hosting. And if you come up with some good idea for a good project, we are always here to help you. And the most important part is to sensitize the citizens with scientific temper and encourage them to participate in science projects rather than just spend their time on digital and social media. They can spend some of that time in actually helping scientists discover and understand their science images better. So thank you very much. So this is our official website called pkc.org.in. The 1 Million Galaxy project is hosted on this second link, which is csa.pkc.org.in. And then if you scan the QR on the top, you will be directed to the 1 Million Galaxies link or a web page. Apart from that, there are some other platforms like Zooniverse or NASA Citizen Science where you can participate. Now, if you have any questions, I would be very happy to take them. I will be sharing this presentation with Mr. Sovanacharya. He will be able to share it with all of you. And if you have any questions, I'm also added in the group. So if you are a part of the WhatsApp group, I will be able to talk there as well. If you have any questions quickly right now, please go ahead and ask. I'm around.
Yeah. Hello, Atharva.
Yes, hi.
Hi, Atharva. I'm Gourav. First of all,
Yes, yes.
thank you very much for this wonderful talk. It's nicely explained.
Thank you.
So I just wanted to inquire because few of my students, few of my colleagues, they are asking whether there is any limit of how many galaxies they can classify once they join this project.
There is no limit. So right now what happens is we have configured the interface to remove the galaxies from the list after 100 responses are received. So once 100 people look at a galaxy, we don't want too many people to keep looking at the same galaxy. It is counterproductive. So we are removing the galaxies after 100 responses. So currently there are some 1600 galaxies that people can classify. So Sudhanshu and I are going to upload a new set of galaxies probably by the end of this month. So we plan to upload 3 to 4,000 more galaxies. So once that is done, people will be able to classify those as well. So we are not uploading all of the galaxies once, but we are uploading them in stages. And we are trying
so maximum around 1600 person can at present classify.
At present classify, yes, yes.
Okay.
Yes.
Sure. Thank you.
No problem. So if there are no more questions, I can hand over to the next speaker, I think. No problem. Most welcome. So I will share the link of this presentation in the chat, so one can look at the slides later on. Okay, thank you so much.
Thank you so much, Mr. Aritra, for introducing me. Can I share my screen? Is my screen visible?
Yes. We can hear you clear and screen is visible.
Thank you so much.
Yes.
So I am just going to give you a very layman's introduction to imaging planets. It's not very difficult. If a person who has not even been active in science can do this, I think anybody else can take up a telescope and do this. So I would like to encourage everybody who has been connected with these citizen science projects and doing so much groundwork for the science community. You can also take up a telescope, maybe an 8-inch Dobsonian, which is a very reasonably priced telescope, and you can image planets from whichever city you are. I live in New Delhi, by the way, and my southeast balcony is full of light pollution. You can imagine living in Delhi. These are the planets that I have imaged from my home balcony. including the sun and the moon. So it is very much possible to do astrophotography and take quality pictures from a bottle 9 skies like mine in Delhi. So I would just take you through a couple of things that you might already have, you might already own, and you can use those items to take these kind of images. So everybody good to go? Hello? Okay. Great, thank you. So anybody, if anybody can unmute and say that if they have a telescope at home, do they own a telescope? Have they ever looked through a telescope? That will be encouraging, and I can, explain in detail what a telescope does and how you image from telescope. Anybody would like to unmute and say if they own a telescope, whichever form or kind it would be? Nobody has a telescope?
Hello, ma'am.
Yeah, hi.
Hi, my name is Ashwin and I live in Mangalore.
Okay.
I own a 10-inch Dobsonian.
Oh, fantastic. And it's a manual Dobsonian that you own?
That's right.
Wonderful, wonderful. So it's very reassuring that somebody knows what a Dobsonian looks like. And the image that is on your screen right now is taken from a manual Dobsonian. Manual Dobsonian simply means that it does not have a tracking. We normally, when we do astrophotography, we use a tracker to counter the Earth's rotation so that the stars stay stable in our frame. So does the moon or the sun or whichever object we are planning to image. So even if you have a manual Dobsonian, you can take these kind of images from your manual Dobsonian. This is a mosaic of around 24 panels of moon. And this was all taken hand-tracked by a manual Dobsonian, which I own, 8-inch Skywatcher Flex Tube Dobsonian. So let's get into the basics of doing astrophotography using a Dobsonian. So first of all, if you take your phone and if you click a frame, you normally just use one photo, one frame. But for planetary imaging or even for solar or even for lunar imaging, we need to use a technique called lucky imaging. In layman's term, lucky imaging simply means that you have to beat the atmospheric distortion, the atmosphere which is between you and the planet. You have to somehow get those frames, get those lucky frames where the atmosphere was stable enough for you to take an image, a sharp image or a detailed image of a planet. So on your screen, what you're seeing right now is Venus. It is very, very tricky planet to image. This is a real-time video of me imaging Venus. This is the stacked image. This is the result of lucky imaging. Basically, we take a video, then we take it to a software called PIPP, and then we process it in AutoStacker, where we stack the frames. We don't have to stack all the frames that we have taken. We take, a chunk of frames. Okay.
Yeah, same issue with my screen. I can only see the first slide right now.
Should I stop sharing and restart again?
Perhaps, yes.
Okay. Somehow it's not showing my presentation. In my Windows tab, the presentation which I've opened is not visible. So that's the problem.
Ma'am, you could choose the entire screen option for sharing.
It's not showing even there. I checked.
I see.
Very strange. Just give me a moment, please. Let me sort it out. Is it visible now? Okay, let me put it to screen. So is it now visible? Can you see the lucky imaging part?
Yes.
It is again stuck. Nothing is moving.
No, ma'am.
Oops. I am actually doing my full. Is it showing?
Lucky image.
Is it showing now? Okay. So are you able to see my whole presentation or just one slide? And now?
And whole presentation.
Can you see lucky imaging?
Yes, ma'am.
Can you see Venus night right now? That's it. If I move to the next, is it showing next?
No, ma'am.
Is it showing planetary imaging using a mobile phone?
No, ma'am.
Yeah, but then it is showing the complete PPT. Now I want to just show you the slides that I'm using. It is in presentation mode. Now is it showing? Can you see lucky imaging now? Now is it not showing lucky imaging? Okay, wonderful. Okay, we are good to go. Sorry for that technical glitch. So anybody has any questions about lucky imaging? I did explain. If anybody wants to stop and ask any question, please feel free to do so. I guess not. Should we proceed? So this is how a video of a Venus looks like. Once you've taken the video, you can then go to various, there are free softwares that I would mention at the end of the presentation, which you can freely download, and you can stack these images and you get sharp images of planets or sun or moon. So let's begin with what we have already. If, like the other gentleman said, he has a 10-inch manual Dobsonian. So this is what my 8-inch manual Dobsonian looks like. You can see there is a adapter on it, and you can see my mobile phone hanging there in front of the eyepiece. So very, very simple. It's not difficult to take images like this. The planet or the object that you're planning to take, you just have to have it in the field of view in your eyepiece. Once you have it in your eyepiece, just attach the mobile phone, the smart mobile phone which you have, whichever brand it is, doesn't matter. As long as you can shoot video through it, you're good to go. So this is what the planets will look like. This is when I started my journey. This is way back in 2020. This is what Jupiter will look like. You can see the 4 Galilean moons along with Jupiter. You can see a few hint of the Jupiter equatorial bands also. This is what Mars looked like when first I saw it on 5th of June 2020. This is what Mars looked like. And this is, of course, Saturn, the Lord of the Rings. This is how it looked like through my mobile camera attached to my telescope. So these are the videos that I took, and you see a lot of movement in Saturn. It's very simple because it's a manual Dobsonian. I am trying to get at the most possible frames through my manual Dobsonian. So I had to move the position of my Dobsonian to ensure that it kind of aligns to the camera of the mobile phone. So few pointers if you want to do mobile astrophotography using a telescope. So you have to use a technique called drift and align. So ensure that the planet comes on the screen which is shown on this slide, and let it drift, let it go out of the screen. Once it goes out, realign and ensure that again it enters into the frame, and let it drift away. At best, you can use a magnification of 9 mm eyepiece. You can also use 6.5, but recommended is 9 mm. This is all through my trial and error method. This is all through what I have learned when I started my journey in astrophotography. Use zoom. So there is an inbuilt feature in all of the smartphones that we use today. Just if you look at the screen of my phone, just up the video tab, there is 1x written there. All you need to do is ensure that you move it to 2x. If you become greedy, if you think that, if you move it to 5x or 10x zoom, you will get a much better image. Forget about it. All you're gathering is a lot of noise. So stick to 2x, which is a very conservative way of lucky imaging. Stick to 2x and you'll get fabulous results. So this is the partial solar eclipse, which I captured through my mobile phone using my telescope. This was in New Delhi. This is how a Saturn final image looks like after you do lucky imaging, meaning you take video of Saturn and then you stack it, and this is the result that you get. This is all using an iPhone XS and my 8-inch manual Dobsonian. This is how Jupiter would look like. You can see the shadow of a moon transiting. Most likely, it would have been Ganymede. You can also see a hint of the GRS, Great Red Spot. This is again an image of Saturn. This is all mobile astrophotography using a very cheap mobile adapter, which I found on Amazon, around 700, 800 rupees. You just have to use a decent eyepiece and you get these images. This is again Jupiter. This is moon. And you can also image moon through mobile phone. You get a good sharp quality image. You don't need expensive cameras or expensive lenses to image your solar system. In Saturn, you can easily classify the Cassini division. This is all mobile astrophotography. There is no complexity. There's nothing complex involved in this. Again, Jupiter with moon transiting, moon shadow transiting. So this is what you can achieve using a mobile phone, which you already own, and a telescope. Moving on to another transition which I took was I had a DSLR already lying at my home. I had never used it. This is a Nikon D5000 model which I had. The image shows the DSLR body without a lens, because now your telescope becomes a lens. This is the T-ring at the bottom. That ring that is shown in the picture is the T-ring, which you attach in order to make it usable or attachable to your telescope. This is how the train looked like, the imaging train with my manual Dobsonian and a DSLR. I had to use an eyepiece projection technique because I was not able to, the back focus was so much that I was not able to get the object in the sensor of the DSLR. So I used eyepiece projection technique. There is an adapter, which is again very cheap, available freely on various retailers in India. You just have to insert a 9 mm or a 6.5 mm eyepiece in that, and the object automatically comes to your back of the screen of the DSLR, and you can again, with lucky imaging, you take a video of the planet and then you stack it using various free softwares. This is what Jupiter looked like through my DSLR, again video mode and stacking. This is how Mars looked like through a DSLR using a telescope as a lens. This is what Saturn looked like. This is Venus, one of the sharpest image, and I improvised when I was looking through Venus through my DSLR. Venus is very, very bright object. It's very difficult to make out any kind of cloud structure or any kind of feature on Venus. I used a moon filter, which I had lying. I used a moon filter to get at least, some kind of feature or sharpness in the edges of Venus, which is again one of the most difficult planets to image, Venus. So once I moved on from DSLR, I found that planetary cameras were game changers. Planetary cameras are in fact cheaper than a DSLR. These are the camera that I used at that time when I bought it was 38,000. Now that is available at around 25,000. Planetary cameras are specifically meant for imaging planets of our solar system. The FPS, which is frame per second, is very, very good. The sensor is actually meant for capturing planetary data. The frame per second ensures that you beat the atmospheric distortion and you take maximum number of frames, and you can process and you can get a fantastic image through a planetary camera and your telescope. This is what my setup looked like once I introduced the planetary camera. And is my mouse visible? The pointer is visible to everybody? So this is the camera. This is the USB 3 cable, which goes through my laptop. Now, one thing you all have to be very mindful if you are switching to a planetary camera, there is no back screen here. So when we were using mobile cameras, we could see the object come into the screen and let it drift away again, realign. And even DSLR has a screen behind. But when you start using a planetary camera, just ensure that you would be, first of all, you will be very awkward. You will not be able to see the object because the screen transfers to here. Now you will have to look at your laptop and you will have to ensure that the object straight away comes to your sensor chip. Couple of days I was very disappointed because the sensor chip on a planetary camera is very, very small as compared to a DSLR sensor or even a mobile camera. I was not able to get the object show up on the screen. So I had to devise a couple of things myself to ensure that whenever I'm inserting the planetary camera, I'm able to see the object on my screen. So the first key point was this is the finder scope of a manual Dobsonian. First, ensure that your finder scope is very well aligned with your eyepiece. There is no room for error here. It has to be 100% aligned, both of these. Then you ensure that you use a 9 mm eyepiece to get the object centered in that eyepiece, and ensure, again, check in the finder scope, it has to be completely aligned with it. Once you've done that, move on to a 6.5 mm, because initially you will need a lot of practice. Once you are practiced, then you will probably not have to change so many eyepieces. But initially I did change a couple of eyepieces to ensure that what I'm seeing here is also being seen in the finder scope, because once the camera is inserted, there is no way that you can use this secondary mirror to find out where your object is. So the idea was to then introduce a Barlow. The Barlow will definitely change the focal plane. The planet would definitely shift. That shift you can see in your finder scope. A lot of finder scopes have a crosshair function. So you can take a mental note and see where the planet was visible, which part of the crosshair it was. Either it's completely centered or it was a little right or left. You have to make mental notes to ensure that, both of these things are aligned. So once you've aligned it with your Barlow, then it's very simple. You just insert the camera, and most likely you will see Saturn like, you see here, and it'll drift away because you're using a manual setup. There is no tracking on my Dobsonian. So all you have to do is nudge a little bit, ensure that the finder scope, where you saw Saturn in the finder scope. Once you take it back to that position, it'll automatically come here. You will be able to see the object here. This is what an actual recording. I use a software called Shourjya. This is what exactly looks like when you are capturing planets through your manual Dobsonian. I use this region of interest, or ROI, the pan and tilt function, to ensure that I get the object stayed in my field of view or on my sensor chip as long as possible. So I keep on shifting that. This is what the histogram looks like. Just ensure that most of the things remain default, barring the exposure. The exposure has to be, very less. The gain has to be somewhere more than 50%, probably 60 to 70%. Ensure that the frame rate is clicked as maximum. The high speed mode is on. So these are the normal settings that you should have. You should always, if you're shooting with an OAC, which is a one-shot color camera, ensure that you're using RGB24. A lot of people do use AVI as the output format, which I also do. A lot of people do use SER format, but then again, it's your choice depending on the SSD drive that you're using on your laptop. You need to be mindful of that. So this is what actual recording of a planetary imaging looks like when you're imaging through a planetary camera. These are some of the images. These are manually tracked. I did not have an EQ platform till about a year and a half when I started imaging. So this is Mars at its best in 2020. These are manually tracked images. And the color that you see here, the blue color, this is not any, this is not a chromatic aberration. This is the CO2 cloud band, and this is the southern polar region of Mars. These bands were visible in most of big known planetary imagers also. So this is not a chromatic aberration. This is Mars at its best in 2020. Again, this is Mars. You can see the aberration has changed. The phase has set in. Most of the arc second, the size of Mars has shrinked a bit. And again, you see a lot of CO2. The southern polar ice cap has shrunk, mean it was summertime in Mars. This is what I could image from my light polluted skies in Delhi using Lucky Imaging. Another picture of Mars where prominently you can see the largest volcano known in our solar system. This is Olympus Mons. This is again Mars, and it is showing a lot of CO2 clouds, normally known as Oort clouds. I was able to see these Oort clouds through my eyepiece also before I started imaging. In this, you see Olympus Mons, and you also see the band of Oort clouds, which I just explained. It was a moment which is unforgettable in my memory. I could see it through my eyes, and I had goosebumps looking at these Oort clouds through my small 8-inch Dobsonian. This is again an image of Mars, all manually tracked. I did not have a tracker that time. And this is what Lucky Imaging and a planetary camera could do. You can get fabulous images under any bottle skies, and planets and lunar and solar surface is not very difficult to image. This is Saturn. Again, this is a very rare image because if you look very carefully on this image, this is the transit of Tethys. Tethys is one of the so many moons around Saturn. So you could see Tethys transiting the surface of Saturn. This was again imaged from my balcony in Delhi. The other 3 moons are also visible. I learned a technique to ensure that I get moons because I was using high gain. So if you're using high gain in your camera settings, most likely all the nearby things, like Saturn has so many moons around, they will be visible once you start post-processing your data. This is what Saturn looks like. The bands, very clear, very striking. The Cassini division, the rings are very, very visible. This is an 8-inch aperture, by the way. So this is again Saturn with its surrounding moons. This is a mono camera that I've recently acquired, and this planetary season, I intend to do a lot of mono imaging of planets. This is Jupiter. You can see the transition from the image, which I took from using a mobile phone, then I took from a DSLR, and this is what a planetary camera does. It gives you very, very clear, sharp images of planets. This is, if you look at Ganymede also, you can see a lot of surface structure. Ganymede also shows a lot of surface structure when you're imaging it. This is the shadow of Ganymede only. And these are, I think this is Io, and this could be Europa. This is an image which got me the Solar System Category Award, Indian Astrophotographer of the Year. This is the Io's shadow transiting the Great Red Spot, and this is Ganymede lurking behind. This is the sharpest image that I have taken so far using my 8-inch manual Dobsonian. You can see a lot of the southern and the northern equatorial belt region, the active regions on Jupiter. I mean, Jupiter in itself is a very active planet, but here you can distinctly see the white pearls, the eye of the GRS, and a lot of colors around the northern equatorial belt and the uppermost region also. This is lunar surface, which I think one of the most detailed image that I have taken from my 8-inch Dobsonian. This is a mineral moon, which you can get if you're using a one-shot color camera. You can take an image like this. You just have to stitch the panels, which is again very automated process in Photoshop. This is very easy to do. This is the partial lunar eclipse, which happened, I think, last year in 2023 in Delhi. I was able to not only witness it, but I was able to image it using my Dobsonian. One of the features of the lunar surface. This is again a mineral moon. This is one of the very interesting pictures. I think this would be one of my best solar images so far. This is the image of a sunspot. The umbra and penumbra areas are very, very well defined. I used a mono camera for this, and I used an IR filter specifically for this image, and you can see a lot of granulation of the solar surface. This remains one of the best detailed image that I have taken of a sunspot from Delhi. This is another angle, and you can see so many details in the sunspot, which normally your eye can't capture. This is one of my recent acquisition. This was on my bucket list to capture ISS transit in front of the sun. I had to drive 30 kilometers away from home. The heat wave was on full. It was 50 degrees temperature outside. It was middle of the day, 2 o'clock. And I'm happy that I did it. It was very adventurous. I could have risked my health, but I loved doing this. So thank you so much. I'm happy to take any questions that you might have. Ashwin Shenoy has raised a hand.
Yes, ma'am. Thank you very much for this talk. I was really looking forward to it. One question I wanted to ask you is how many images do you stack, for example, for that picture of Jupiter?
So, there is a science behind it. Jupiter has a phenomenal rotational time. It is 9 hours and 56 minutes to be
Yes.
precise. So if you start imaging and you take 5 minutes of video of Jupiter, at the end you will get a very blurry image. So there is a classification for Jupiter. You cannot go above 90 seconds. That is 1.5 minutes. For Saturn, you have to restrict yourself to 120 seconds. For Mars, you can go up to 5 minutes because Mars has almost the same rotational speed as Earth has. So basis their rotational speed, it is advisable. For Jupiter, I never exceed 90 seconds. So 90 seconds, that's why I said FPS, meaning frame per second, is the king. You have to ensure that the maximum frame rate that your camera can give you, you are achieving that.
Okay, and this 90 seconds is with the platform?
Yes, 90 second with the platform. Earlier, I was getting a lot of blurry images because I was not able to track Jupiter, and Jupiter is it's not forgiving. Let's just say that immediately if you exceed that time limit, it gives you an image which is quite blurred. I'm sorry for my camera.
Okay. One last question. With the
Sure.
planetary, with the CMOS camera, what kind of exposure times do you give?
So for Jupiter, see, there is a triangle that you have to understand. The triangle is between exposure, gain, and your FPS. So our goal is to have maximum frame per second. So what
Yeah.
we are trying to achieve is that if I lower the exposure and if I use a very small ROI for typically a planetary imager, the best ROI is 640 by 480. That is the region of interest that you should take. So once you do that, you lower the exposure. Maybe it looks very dim on your laptop, but just don't worry. Once you stack the image, the brightness and the features will come out. The signal to noise ratio will improve once you're stacking the image. But you have to ensure that the frame rate is maximum. So for that, Jupiter, everybody has a different skies and different conditions that you're shooting at. So I would not advise on an exposure time. You just have to maintain the triangle and you just have to ensure that you are achieving the maximum frame per second for best images to capture. I hope that
Okay.
answers.
Yeah, okay. Thank you very much. It does.
You're welcome. I have an Instagram account by the name Astro by Sona. If you have any questions, you can, DM me there. I can probably assist you with your planetary or lunar imaging. If not, I think we'll have the other speaker ready to start the presentation. Thank you so much, everybody. All the best. Clear skies.
Can you hear me? Hello? Thank you so much. I will start my presentation, right? I will turn off my camera because my internet connection is not so good here, right? Thank you. Can you see my screen? Okay. Well, thank you for the opportunity to join this camp. I'm so grateful to be here, and I hope my presentation will be useful for all of us. My name is Cledison Marcos da Silva. I live in Brazil. I will show you two citizen science projects to participate from the comfort of our house. Who am I? I'm a citizen scientist with primary interest in variable stars. I have a degree in pedagogy and physics and postgraduate degree in teaching astronomy and natural science. My studies are related to variable stars, performing CCD photometry and visual observations and reporting to AVSO, contributing to international research and campaigns related to the stars. I'm also involved in other Zooniverse projects such as Black Hole Hunters, Kilonova Seekers, and Planet Hunters tests, among others. I'm also a collaborator of the Hunting Outbursting Young Stars project, which observes star-forming regions with the aim to study of their members, and possible members. My associations are AAVSO and Variable Star South. The AAVSO is from USA, and Variable Star South is from New Zealand. Well, what people think we need to do citizen science? Large telescopes, high technology, and everything else. But we need, in these cases, a computer, a cell phone, or even a tablet. Well, the first project I will show you is this detective. In this project, available in Zooniverse platform, you search for nearby stars where planets form and dwell. What is disks? Disks are these, quite similar to galaxies, but they're not galaxies. They are stars surrounded by dust and gas. And you can see these gaps on some of them. And you know that here we are seeing planets forming, right? You are seeing newborn stars and newborn planets. There is a vast shape of it. You can see disks, spiral, you can see edge on disks, you can see dusties, disks, you can see quite similar to galaxies. You can see all of these patterns, different patterns of the of what we are looking for. So what you need to do, you will open Zooniverse platform, you will search for this detective, and you will open the class. Then I show you how to do it. But the main page is it. You will see a bunch of images and some options. You will click on it. You will play the video. You will analyze the image, and you will select some of these options to do your classification. Well, you will need to look for in some web pages like Simbad to see if your object is already studied, if it is known, what type of object it is. In this case, is a young stellar object candidate. You will also need to look at Vizier. There is if your object is not in Simbad, it will be in Vizier. So if you think an object is a good candidate, you can report through this this formulary that we call think you've got one. You will fill all these options and you will report to the team. If you don't, no problem, because we will know your classification. You know what you did in the flipbook, but it will take longer. With this form, your classification will be seen faster. So I will show you how to do from here. It's fast. Well, this is the main page of the project. You can see here the number of subjects we have available, the number of completed subjects, and you will need to join Zooniverse, creating your account, and you will click on classify. The flipbook is here. You can click on play and travel through the image, or you can click in image by image, right? You will see here that the object looks good in all the images, but in WISE 3, you can see a kind of contamination here. In this case, I will flag it as extended by the contamination. From here, you can click on done and pass to another subject, or click on done and talk and tell us what you see. I will click done. Another subject will be open. You do the same. You travel through the image, and you can see is also extended. There is a field guide here on the right of the screen. You can read all of this information. And done. One more time. Well, this one looks good. You can see the object is the only one inside the circle, so there is no multiple. You can see it's quite round in all the images. It's two mass, and is not extended. So I will flag this as none of the above, and I will click done and tap. This is enough. You can submit it if you want. So what you need to do, you will click on the metadata. You will open Sinbad. The object is not there. So you will open this here if you want, because you need some information here to fill the report. I'm sorry for my slow connection. As you remember, I clicked on none of the above, right? The first question. The second is, what is the subject number? You will get this information here, and you will copy and paste it here. What is the WISE ID of the object? You can see this information clicking on the metadata, and here it is. Is the number started with J. Paste it. Is the object in Sinbad? No, we checked it. There is references? No, the object is not in Sinbad. Does this object have a parallax? We will see on Vision. DR3 catalog, right? You search for DR3. Gaia EDR3, right? You will keep on looking for. And you will find it here. Main source, Gaia Collaboration 2022. And here's the parallax, PLC, PLX. You will copy it, the error also. Yes. You will paste it, the parallax and the error. Anything else about the subject? Let's leave this empty. You will fill here with your name, your Zooniverse ID is, I will comment here. You see your Zooniverse ID below your name. Is here. Right? And your email address. Send. Okay. You submit it. So now the subject will to an intern database and the team will verify it following the process. You can keep on classifying by clicking on classify. Another subject will be opened and you will do the same. If you need questions, you can tag the moderators, commenting on talk, and we will see you're asking for help. In this case, we can see multiple inner inside the inner circle and multiple outer, right? You can do the same. Click done or click done and talk. Okay, this is the first project, and in this case of this detective, you can help to find disks, and you can see here the result page, all the discoveries of the project. The project in 2.0 phase, and your discovery will be listed here if you help with one. Let's go to the second project. The second project is Exoplanet Watch. And here, in the first project, you studied the planet forming regions, right? And here, you will help to study already known exoplanets. You will not discover exoplanet here. You will help to study already known exoplanets. Starting, you will to the website. You will learn about exoplanets. You can join the community. To observe, you can use your own telescope and another telescope to get data. You will analyze your data and you will upload to get recognition of your data. If you have your own telescope, you can do your own observations. You can join the Exoplanet Watch Beginner Observation Campaign in June 2024. To the Northern Hemisphere, we have these two planets, Capt 4AB, and this 8B, 189730b. To the Southern Hemisphere, you have the same planet and WASP 178b. You can do your own image, and submit it to AAVSO and to Exoplanet Watch. If you don't have your telescope, no problem. You don't need to have your own telescope to participate in Exoplanet Watch. Submit your email to check out exoplanet observations data from robotic telescopes that you can reduce and submit it to AAVSO. You only need to open the page and paste your email here and submit it. And the data will be sent to your email account. You will upload it to your Google Drive, the only thing you need, and then use this exotic to analyze your data and create your light curve. There is a Google Colab Cloud version of exotic, but you can also download it to your computer. But the project recommends you to use the Colab version. That is this. Is a Python code, but there is tutorials to teach you how to use, and also it will show you what to do. It's quite simple. I cannot do this because the first step here is quite slow, and we have to restart several times. So it will take some minutes of our presentation. But you can follow the Slack channel. You can join the Slack channel and ask there for help or instructions. Well, after the you analyze your data, and then it will create your light curve here from WASP52B. Right, this is the light curve. You can see here the transit when the planet passes in front of the star. It blocks the light of the star, and there is a beam. There is a dip here, and the planet exits to the front of the stars, and the bright return to what it was before. Well, this is the report you will submit to AAVSO. It has all the information about the planet, all the times, all the direction, and everything the report needs. And here's the submission page. You will need to fill the select site and equipment. You will report this report, and an image it will send to your Google Drive account. And then it will be available in AFVSO page and Exoplanet Watch page. It's the same planet, the same light curve. All the light curves I sent to AFVSO. This is the planet. Here's the date of observation. You can see 2022, 2011, all past observations. And here's the database. You can see my code there to this light curve. It's quite simple, but if you commit some mistake, don't worry, because it's part of the learning process. And here all the contributions of citizen scientists. And here all the observations of this exoplanet. All the contributors listed here. Once you submitted your report to AVSO and Exoplanet Watch, you can get a citation and acknowledgement. If you use any Exoplanet Watch data in your publication, you are required to include the observers of those data as co-authors on your paper. To get in touch with your anonymous observer, contact the AVSO with their observer code. So if someone used your light curve in a paper, you will be listed as co-author and contributed to the science of exoplanets. This is my brief observation. This is my brief presentation, and I want to thank you the opportunity.
Sir, can you please share the link with us?
I will. The Exoplanet Watch and this is the tactic. Mhm.
Yeah. Like I want to ask that is there any Python background necessary for contributing in that exoplanet watcher? Or and if someone is complete beginner, so can he also contribute it?
On the site of the Exoplanet Watch, you will see a beginner tutorial that will teach everything you need to run the code. But it's not hard. It's quite simple. You don't need to worry because you only run the cells. The code is already done. You will only run the cells. There is no difficulty.
Yeah. Okay, sir. Thank you.
Welcome. I think she's muted. I just want to say sorry for my brief presentation, but I'm passing through a disease problem, and I did it fast because I'm in a moment of thank you so much. But if you have more questions, you can follow me on Instagram with my name, Cledison Marcos da Silva. You can add me on Facebook, right? And I will be ready to help every one of you that need. Okay. Thank you so much.